quantum computing offers over the long term, and it is one of those amazing technologies that has the potential to really have a global impact. So that's very interesting. In terms of the initiative in the digital economy, it's probably quite obvious to most people here, but quantum computing is, effectively a very digital type of technology. And that makes it very interesting. It's not the same as making steel and concrete and physical things. Although what we're actually trying to do in some of the labs around the world and here at MIT is actually very physical as well. So from a business point of view, those two things and the intersection of them are very interesting. And then I would say that of all those areas that I've talked about, my particular interest is in what's called nascent markets. And these are brand new markets that emerge into the economy. And they're quite well known for having a lot of ambiguity and complexity. But for most of those markets, if you think about something like Uber introducing the ride-hailing market, there's a lot of complexity, ambiguity, but they knew that cars could be driven and they knew people could use mobile phones. So as much complexity and ambiguity as there was in that nascent market, it pales in comparison to the complexity and ambiguity that's inherent in quantum computing. So that sounds like a real challenge, and that's what drew me into being interested in it. And then the final bit I'd add is that I feel very lucky to be in the Sloan School of Management. There's very few places, I think you could probably count them on one hand, where you have a business school that is in the same institution as having world-class researchers in quantum computing. And so, to some degree, I feel it's a challenge for us that here at MIT and at Sloan, we need to step up to and be the community that's leading the thinking on the business of quantum computing. So that's kind of what brought me here today.
Hey, everybody. My name is Dirk England. I'm a faculty here in electrical engineering and computer science. I started majoring at Caltech in physics and math, and I was interested in understanding the universe better. I was initially going towards cosmology, but then towards my junior year, I was sort of missing the constructiveness of experimental research, or being able to do an experiment, not just observe, but actually do an experiment, and by that way try to understand nature better. And then I joined the laboratory of Hideo Mabuchi, who had just started at that time in atomic physics, working at that time with Jeff Kimball. They had sort of a joint group. And so as a junior, I started to work in the lab, and it was fascinating that, like, you could, on the tabletop, you could explore the frontiers of physics right in front of you. You didn't have to look up in the stars. And much of what sort of expresses that was a different way of fundamental physics that touches on information theory. Really, information theory might be the best way to describe the basic principles of physics. And in this way, really, I started to go into atomic physics, and then was thinking about Cambridge for grad school versus Stanford. I ended up going with the weather, so I went to Stanford, and I had this third connection here to Yoshi Yamamoto. I was joining at the time when Yoshi was just setting up a new experiment, and I would say I was going to, so at Stanford you can rotate, and so I was going to do Jelena Vukovic first, who was just starting her new group at that point, and then Yoshi after that. And I never left Jelena's group. And so I stayed in semiconductor quantum optics, and it's been going from here. But it's also a fantastic community, I would say, in quantum information science and in atomic molecular optical physics in particular. And so I think it's been a fantastic ride for me last 20 or so years in this field, and it's amazing. And it's a big surprise to see so many people now, so many young, awesome people who are going into this field now. I want to echo what Ike said also. Like, I think a lot of us initially were drawn into that field in part because it was unexplored. And so in quantum computing, and in this field in general, there are still so many fields that are unexplored. I don't follow the Troughton path. Like, there are many other directions to explore that in one way or another are connected to quantum computing. Quantum computing is much more than making a faster algorithm. It really teaches us about the fundamentals of nature. And so there's a lot to do.
Thank you all for telling us some of the things that inspired you to get here. So I'd like to go from the past to the present. And if you're willing, I'd like you to tell me one interesting question that you're trying to answer in your lab or group right now. Donna, if you'd like to start again, you're welcome to.
Sure. So what my lab does is we use chemistry for quantum information science. So we use the ability to put atoms exactly where you want to control both physical and electronic structure. And that's kind of great for quantum properties because precise control is everything that we talk about. Most of our work is focused on quantum sensing. And right now, actually, where I was half an hour ago was working on a manuscript draft that I'm really excited about, predicting whether a molecule where you can read out spin information can sense a local magnetic field of, for example, a 2D magnetic material like chromium triiodide. So the space between the surface of the material and, let's say, 10 nanometers away is essentially a completely blank space. Nobody knows what happens there. And so if you can get this tiny molecule right down there, you can start to answer questions about what happens to a local magnetic field in a 2D material. So both understanding those properties and designing molecules that interface with questions like that is something that we're really excited about. And we're also excited about a lot of biological applications that I would be happy to talk about. But thinking about the magnetic field at chromium triiodide and whether quantum sensing in a molecule can help with that is probably where my head is at this particular moment in time.
Could you elaborate on one aspect of that? I'm really fascinated by the use of sensors in this odd way. How does the field of quantum information science and quantum computing help in the kind of vision that you just described?
So that's a good question. I'm not sure I would call it quantum information, right? Quantum technology, broadly speaking. But so the way that you would read out a magnetic field locally, and we could have an extensive discussion about what quantum means that I think you would have a lot of insight into. By modulating so you're creating a local magnetic field and you're changing your splitting of your m sub s levels, and you're changing not just your axial splitting, but your rhombic splitting as well. And so that should give you, especially because you can specifically orient molecules relative to a surface, that should give you spatial resolution for the magnetic field. And so optically reading out this information, just like NV centers, you should be able to get an optical probe. Now, is changing the separation of m sub s levels truly quantum? That's broad discussion.
I think I would agree with you, but if I may translate you.
Oh, yes,
Let
sorry.
me see if I got the translation correct. Does this mean that an iQuackathon student who's working with Qiskit might be able to come up with a sequence of control pulses for your molecular system?
Yes.
Which would then contort it in such a way that it'd be able to sense better?
Yes, quite possibly. That is a really great suggestion. And because I'm a chemist, a lot of the actual quantum operations we do aren't necessarily more sophisticated than what a, protein structural biologist would do with nuclear magnetic resonance to decipher structure. You do a lot of correlative spectroscopy. And we were just talking before the panel started about one of the pioneers of this field, Alex Pines. And so the library of ways to control pulses and magnetic resonance is broad. And my lab effectively steals that existing technology because our main contribution is making and designing the things, and then we borrow the technology. But there's this amazing space in between that Ike is really pointing to, with the ability to control this at a more sophisticated level.
So your message to our audience here and out in the virtual world might be that everything you're doing that you think is working on quantum computation could actually make chemistry better.
Yes.
Oh, there's a but coming.
There's a giant caveat. One of my personal crusades that I think at least Will has been unfortunately subjected to is that the space of quantum computing as applied to chemistry requires more caveats than is frequently expressed.
What's one of those caveats, though? Because actually, the reason I'm keeping you from going on is so that I can say less later, but also because this is important to y'all. I think what Donna is doing is actually useful. Okay. Seriously.
That's good. I'm not sure I do.
But like more useful than a lot of what's happening in quantum computing today. So what are one of the caveats? Because really, there are real big problems.
Yeah, so I would say that the phrasing the questions correctly is really important. So one of the, so to pick on approximately half of the sponsors of this event, one of the classic things that you'll see for why quantum computing is useful is to understand things like the mechanism of nitrogenase. I mean, have you seen these slightly horrifying Google videos with some guy standing in front of a cornfield? Anyway, there is an enzyme that turns N2 into ammonia. It uses the process that we use commercially, the Haber-Bosch process, uses 2% of the world's energy, et cetera. This is very close to my field. But the problem is the argument that you're going to use a quantum computer to find the ground state of a catalyst to understand it better does not hold water, because the ground state is intrinsically not the thing that does the thing, right?